started. Thank you so much for pointing that out. I'm giving my spiel here. We have some very exciting demonstrations planned. We've got some of my favorite combustion reactions over here on this side of the table, and I've got some of my very favorite extremely cold science experiments over here on the other side of the table. And today we're going to take these experiments, some of which we've seen before, some of which are new, and we're going to have a battle between fire versus ice. So if you've seen our combustion show before, or possibly seen us work with some dry ice on Echo Live in the past, that's awesome. I hope that you will be able to put your prior knowledge of all of these science demonstrations to the test and answer all my questions as we move through this program. If you haven't done so already, go ahead and introduce yourself in the chat. That way you know you'll be able to answer and ask questions throughout the program about any of our really exciting science demonstrations and experiments. If this is your first time tuning in, you are in for a special treat because I've chosen some of our biggest and best and most exciting chemistry reactions here. So we said we're doing fire versus ice. So I've got some different kind of challenges that we can try out here. The first one is which one can create the better colorful chemistry reaction. So we've done colorful chemistry using our combustion reactions before. What we have inside these 3 spray bottles are some inorganic salts. So basically inside each of these spray bottles is a different metal combined into a salt solution and then dissolved into ethanol so that we can spray it through a flame, which is going to give us a very cool, very interesting, colorful chemistry reaction. Now let me go ahead and change my virtual background here because these metals, right, are metals that we would find on our periodic table. And the reason that these metals create colorful chemistry reactions is because of where they lie. The periodic table is designed in a specific way that tells us about the number of protons and the number of electrons that each of these elements possesses. Now, depending on the orientation or the location of the electrons orbiting around these different metals in their atomized form, we will get a different wavelength of light emitted when we put them through a flame. So electrons, just like on my shirt, right, are constantly orbiting around the outside of atoms. If we give them some energy, like in our combustion reaction, which we're about to do, the final product could be light. So we'll be able to see these a little bit better, actually, if I turn off my virtual background. So I'll go ahead and turn off my virtual background. And then, of course, if we're working with chemistry, or especially working with fire, I also need to go ahead and put on a little bit of safety equipment. I'm already wearing my lab coat today. I've already gone ahead and secured my hair off to the side so that it's not going to go near any of the flames that I'm working with today. I'll go ahead and put on my safety goggles right now. And then I also have this very handy dandy, pair of gloves in order to keep me safe from all of the dangerous chemistry that we're doing here today. Now, we should probably preface that we should never ever play with fire at home. So while I wouldn't recommend that we ever play with fire or recreate any of these fire experiments, that's the point of tuning into Echo Live so that you can get an up-close look at this maybe a little bit dangerous side of chemistry in a safe way. So we'll go ahead and light my Bunsen burner here, and you might be able to see that this butane torch burns blue. So butane is another kind of chemical, and when it is burning, it appears blue. But let's take a look at our first flame salt, or our first metal salt, which is strontium. So let's go ahead and see what color strontium burns when we spray it through this butane flame. Let's see. We get a very, very cool bright orange color. Does anyone remember out on Echo Live, does anyone remember where we find strontium in daily life, where we might have seen it before? Maybe use your prior knowledge of what you know strontium is used for, or remember what we told you on a past episode of Echo Live. Does anyone remember? If you do, go ahead and type it in the chat. Our next metal is lithium. So lithium will burn a different color than strontium. Let's take a look. And this one burns a very, very hot pink color. So lithium burns hot pink. if we haven't said so already, we find strontium in road flares. So strontium is found in road flares, so that orange flame might look pretty familiar to you. And lithium is used in cell phone batteries or electronic batteries. So lithium ion batteries contain lithium and may look pink if they ever were to catch on fire, which would be really, really bad. Our last one is going to burn green. So I'll spray it through the flame. We'll take a look and then tell me, do you remember which metal salt this one is that burns green? This one's my favorite by far. Does anyone remember which of our metal salts burns green? Go ahead and tell me in the chat if you remember. Go ahead and turn off my butane torch here. There we go. Awesome answers, everybody. It is, in fact, copper. And someone in Zoom even told me that with their prior knowledge that it is the same metal we used to coat pennies and the same metal that we built the Statue of Liberty out of. Great answer, everybody. So pennies are orange, right? So we most commonly think of copper as being that very noticeable orange color, very shiny. But over time, it will oxidize. It goes through a really slow version of what we just did. And when copper oxidizes or is burnt in combustion, it turns green, which is what happened to the Statue of Liberty over many, many years. Good job, you guys. You're really impressing me with all these really great answers. So that was our first colorful chemistry reaction. That one was fire. So keep that one in mind. But let's go ahead and try a colorful chemistry reaction using our dry ice. Does anyone remember? What is dry ice? Does anyone know what is the chemical composition or what is being turned into ice for our dry ice there? Don't worry, Libby, I can see your comments coming in Zoom. Don't you worry, and I can see everybody else's too. Go ahead and tell me, do you remember what dry ice is made out of? Awesome job. Lots of people starting to chime in and to tell me that dry ice is made out of carbon dioxide, which we experience all the time. So if you take a deep breath and exhale, we exhale a fair amount of carbon dioxide gas. At room temperature, carbon dioxide is all around us because it's a gas, but it is invisible and it is colorless and it is odorless. So we can technically feel it. If we wave our hands around in the air, we can almost feel it rushing against our fingers. So we know gases are all around us. But if we really want to be able to see carbon dioxide, we have to turn it into a solid or turn it into an ice cube. Now, I've got some of that dry ice here in my cooler next to the table. But my next question for the audience, do you remember how cold, what temperature do we have to make carbon dioxide gas in order to get it to turn into a solid, like an ice cube? Does anyone remember what is the temperature of dry ice? Ooh, good guesses already starting to come in. Go ahead and tell me in the chat. I'm going to pull out just a little bit of this so that we can take a look at our dry ice. Good answers coming in. Priya tells me negative 321. It's not quite that cold. If you are remembering that, that's actually the temperature of liquid nitrogen. So awesome job. Everyone who's naming that, you really do listen. That is the temperature of liquid nitrogen, which is much, much colder. A couple of people are telling me something correct or really close to correct, that dry ice, this stuff that I have right here in my hand, this stuff is about negative 109 degrees Fahrenheit. Couple of people telling me that they love dry ice, and so do I. This is something that you actually can purchase at certain grocery stores because they sell it for camping so that people can use it when they go camping to keep their stuff very, very cold. Since it's much colder than frozen water, it stays colder much longer. So I've got some of that dry ice right here on my glove, and this glove right is protecting my hand because this stuff is very, very cold. It would sting my hand pretty badly if I touched it with my bare skin, but this stuff is negative 109, and it has to be negative 109 degrees Fahrenheit if we want it to exist as a solid. If it gets any warmer, it will immediately start to turn back into a gas. It actually skips the liquid phase altogether, which is why we call it dry ice. So let's take a look at what that looks like. We'll just go ahead and drop some of it right here inside our large beaker. And we can see that as it starts to warm up, especially since I sped up the process by putting some hot water down in the bottom of this beaker, this stuff is starting to sublimate. It's starting to turn into a gas. We did say that carbon dioxide gas is invisible, right? So we are seeing something here inside the container. This is one of my favorite things to do, is just to touch this substance that we've created. What we're seeing with our eyes is not actually carbon dioxide. What we're seeing is condensed water vapor. So since that stuff is much colder still than the air around it by the time it turns into its gas phase, it will actually condense the water particles in the air and form a cloud, just like we're seeing here inside that beaker. So we'll go ahead and I'm going to set that off to the side because we're actually going to use that a little bit later on. But we said the object of this, right, was to create a colorful chemistry reaction. If we want to do that, let's take a look at the materials that I have down here on this tray. So in this Erlenmeyer flask, which is the name for this type of glassware that's kind of shaped like a cone or a triangle all the way around, inside the flask, I've poured some water, and Jason in Zoom tells me that I've also added universal indicator. It's one of our favorite things to use here on Echo Live because this indicates one of those chemical properties we've talked about in the past. So I've poured some of this universal indicator into the water, which has stained it green. Now, can anyone tell me, what does universal indicator indicate? What do we use it to indicate? Tell me in the chat if you know. What does it measure? What do we use it for? What have we used it for in the past? If you've seen a past episode of Echo Live, what do we use this universal indicator for? Exactly, good answers. This indicates acidity versus alkalinity, or acids versus bases, or acids versus alkaline. So the universal indicator scale looks a little bit like this. Let me pull it up right behind me, and then I'll step out of the way. So here behind me, I have our universal indicator scale. So you can see that it goes from being green in the center. So a pH of 7 is what we want water to be, right? It is neutral. It is not an acid or a base. But if it shifts this direction, if our pH increases, that means that we have formed an alkaline substance, which we also call a base. So it changes from green to blue to darker blue to purple, the more basic it gets. But we can also have a shift in the other direction. We can also have a shift from a pH of 7 down the pH scale, so much lower into these red, oranges, and yellows, which tells us that it is a base. So we're going to drop a little bit of our carbon dioxide into this Erlenmeyer flask with our universal indicator inside and see what kind of pH change we get. So I wish you could see it a little bit better. Maybe if I put it on top of this, it will work. We'll see. So we're going to take just a little piece of our dry ice here because it has to be small enough, obviously, to fit inside our glassware. And then let's take a look at the color change we see. What do you notice? As soon as you notice a color change, or you're able to identify whether this substance being created is an acid or a base, tell me in the chat, is this an acid or a base based on the color change we've seen? Lots of great answers starting to come in. Good job, everybody. Based on the pH scale, which we've noted behind me, we have created some sort of acid here inside the container. What happens is when this carbon dioxide turns from being a solid into a gas, that carbon dioxide gas will actually grab on to some of those hydrogen atoms from the water, which forms carbonic acid, which sounds really scary, but we actually experience carbonic acid pretty often. So carbonic acid is the same acid inside all carbonated beverages. So if you've ever drank seltzer water or soda, that what makes it bubbly and fizzy is carbon dioxide gas. We put carbon dioxide gas inside them to make them bubbly and kind of fun to drink, but it also creates this acid, which is why I'm sure we've all been told that we shouldn't drink soda because it's bad for our teeth. So if your dentist has told you that, now you know it's true, because our universal indicator has shown us just how acidic these substances become when they're exposed to that carbon dioxide gas, which is pretty cool. Now, tell me in the chat, now that we've wrapped up our first 2 colorful chemistry experiments, tell me in the chat, which one did you like better? Were you a fan of fire or were you a fan of ice? So we had our colorful flame salt fireballs, or we have our bubbling over universal indicator reaction here. So tell me what you thought in the chat. Who won this first round of fire versus ice? Ooh, a couple people. I'm getting answers from both sides, which is kind of exciting for me. So a couple people who love the fire reactions, but a few people who love dry ice. These are awesome. Now we've got a few more rounds before we make our final decision of who's the winner here today on Echo Live. The next thing we're going to do is we're going to use fire and ice in order to create explosions, which is pretty easy to do, because in order to create an explosion, all you need is a rapidly expanding gas inside a closed container. So for both of these reactions, I have one of these empty coffee canisters here. So 2 empty coffee canisters. The only thing inside is a little bit of air and a little bit of water. So I've poured a small amount of water, just enough to cover the bottom, into both of our coffee canisters here. This time we'll start with ice. So we'll start with ice this round. And what we saw when we dropped our dry ice into this container, right, is that that solid started to rapidly sublimate, started to rapidly turn into a gas. That's a phase change. When that solid turns into a gas, the molecules pick up kinetic energy and they expand. They take up more space, which we said is just one of the things we need for an explosion. The other thing we need, a closed container, which we can do pretty easily just by sealing the lid here on our coffee canister of science. So let's go ahead and take a little bit of a closer look down here at our first ice explosion. We'll take just a little bit of dry ice from our cooler. We'll drop it down inside our coffee canister of science. A little bit more. And we'll let that gas start to sublimate. Now, you can't see much happening, but I can show you that it's sublimating if I just do that. So we can see that those gases are starting to form. Their molecules are starting to expand, spread out as they gain kinetic energy from the heat around them. Let's go ahead and seal our lid and watch what happens. Whoa, right? We blew the lid off our container. We created an explosion. Let's try that one more time, because as long as we have an expanding gas here, we can do this reaction as many times as we want, because those gases are expanding inside. The pressure builds until it pops the lid right off the coffee canister, creating a pretty controlled, pretty safe explosion. All right, so that is an explosion using just a phase change here. So all we needed was that expanding carbon dioxide gas trapped down there inside our coffee canister. But let's take a look at what fire has to offer this reaction. We'll go ahead and set some materials off to the side here, because this one gets a little bit messy. We've done this one on the past in Echo Live. In this container, we are going to create a carbide cannon, because cannons rely on some sort of explosion, right? So instead of using our dry ice in order to generate that rapidly expanding gas, we are going to have a combustion reaction. We are going to combine fuel, heat, and oxygen all inside this container and ignite them, which is going to rapidly expand the gases inside so quickly that it's going to blow the lid off the coffee canister. I do have my fire extinguisher handy. We've gone ahead and covered up my table because we said this is a little bit messy. Set just a couple more things off to the side so I have a little less cleanup to do later. I've learned my lesson with this one in the past. Now, we said I added just a small amount of water to the bottom of this coffee canister. And if that sounds funny to you, I understand why. Because normally we think of fire and water as not being friends. We think about how water can insulate things from fire, can protect against fire, and we also use water to put out fires. But in this case, the water is going to dissolve this calcium carbide. This calcium carbide is a chemical that when it dissolves in water, it goes through a chemical change, just like our dry ice did. But this time it's going to create acetylene gas. And acetylene gas is super, super flammable, just like it sounds, which is exactly what we want for this reaction. So I'm going to go ahead and before it's too late, I'm going to put on my hearing protection here. Zoom will do a good job of canceling out some of the noise from this explosion because it is going to be quite loud. But if you are startled or bothered by some loud noises, you may want to cover your ears. I'll give you a countdown from 3, 2, 1. I'll make sure you'll be able to see it. So at the end of that countdown, you'll want to cover your ears if you just really don't like loud noises. All right, my hearing protection is on. Go ahead and get my gloves on here. Super important to always stay safe and take safety precautions around fire. All right, we're dissolving our fuel. We'll go ahead and trap that gas inside our container and we will ignite it in 3, 2, 1. This reaction, I will say, loves to do this to me. This is not the first time this has happened, but it's always a good lesson in perseverance. So sometimes in science, we have these things called variables, things that don't go quite right the first time, but we're not going to give up. Don't worry. We're going to go ahead, dump out the ingredients of our reaction, and we'll just start over. So we'll give our water another go. We'll get ready to add all our ingredients. I think we need to do it just a little bit more quickly this time. We'll get our camera zoomed back in over here on our carbide cannon reaction. There we go. All right, a little bit more quickly this time with our reaction. We'll go ahead. We've added our fuel, trap that gas inside. We'll go ahead in 3, 2, 1. Ta-da! This is why we never give up. Otherwise, we wouldn't get to see this amazing explosion created using our combustion reaction. So that's about the end of round 2 of fire versus ice. Now tell me what you think. Who won that round? Was it fire or was it ice? Was it our carbide cannon or our dry ice popping lid? You can tell me in the chat which one you thought was the better, more exciting reaction. Now, explosions are dangerous, and like we said, we would never ever want to play with fire at home. It is totally unsafe, and I would not recommend it. But if you would like to do a safe experiment using explosions, I do have an option that we've talked about here on Echo Live in the past. Like we said, you only need a rapid expansion of gases in a closed container in order to make an explosion. You don't need to use fire. What you can use is some empty film canisters, some Alka-Seltzer, and some water. So this reaction is very simple, but also really, really fun. Let me zoom out just a little bit. That way we get a good view. Now, full disclosure, I've never tried to launch this many film canister rockets at once before, but I'm hoping with just a little bit of your encouragement and maybe some belief in science that we'll get at least most of these film canisters to go off. Our closed container, right, is the film canister. So I've got lids for each of these containers. Before the program, I filled each of these film canisters about halfway full with water. And then the last thing we need is half of a tablet of Alka-Seltzer going into each of our film canisters. So I'm going to do this in rapid succession. I'm going to drop in the Alka-Seltzer, seal the lid, because as that Alka-Seltzer dissolves in the water, it's going to generate carbon dioxide gas. Gases take up more space than solids or liquids, so that gives us the expansion of gases we're looking for here inside our closed containers. So now that we're comfortable with the science, let me take a deep breath here, and we're going to give our, I think, 1, 2, 3, 4, 5, 6, 7, 8, 9 film canister rockets a go. So here we go. One by one. And the pressure, oh no, that pressure is starting to build inside each of our film canisters here. I can see that the canisters are starting to bulge. So we can notice that the pressure is building. And there we go. We had our first rocket launch. We had our second rocket launch. Third rocket launch. Oh no, spilled some water. All right, we've got a couple more. Building pressure. Here we go. In just a few more seconds, we should have all of our film canister reactions starting to go off. There we go. And there it is. So I'd call that a pretty good success. I'd say 7 out of 9 is not bad odds. Maybe with a little bit more time and practice, maybe next time we do this, we can get all of them to go off. But I'd say that went pretty well. This is, again, one of those safe science experiments that you can try at home. Of course, this is still an explosion. It still should be best done outside because you can see it made a little bit of a mess here on my table. But this is one of those experiments that we've listed on the Michigan Science Center's website. If you visit our website and search for at-home science, there are activity guides and experiments that you can try at home using some really, really simple materials. And this Alka-Seltzer rocket reaction is one of my all-time favorites. So a safe version of our explosion reaction. Let's take a look at your comments. Let's see who won the explosion round. Ooh, still we got answers for both. That's so awesome. I see Michelle chose ice because the carbide cannon can be a little scary. Maybe that one's a little safer, but just as cool. Lots of people picking fire. I'm glad we're getting votes for both teams because we've only got 2 experiments left. Now we've done a lot of experiments using fire or ice, but so far we haven't done any experiments where we've combined them or put them together and really pitted them up against each other to see who might win. For that, we've got another reaction that we can try. And what I'm going to do is I'm going to light a series of these tea light candles here, right on the front of the table. Maybe not all of them, but we'll light a good amount of these tea light candles. And this will represent fire in this round of fire versus ice. There we go. All right, so these candles are relying on the same principles that our carbide cannon does. The fuel is provided by the wax on the candle. The heat comes initially from this lighter, but it can actually sustain itself just by burning a little bit longer. And then there's oxygen in the air all around us, which is super important. Otherwise, us people wouldn't be able to live here on Earth. And so all the ingredients for our combustion reaction are represented right here inside our tea candles. But we said we're going to use these in order to test the winner between fire versus ice. So what I've done is in our first reaction using the dry ice, I sublimated some of that dry ice here inside this large beaker. Now, carbon dioxide is actually heavier or more dense than air. And so it actually will always sink to the bottom of our atmosphere, which if we think about it isn't so great, right? We know that lots of machinery will kind of emit carbon dioxide. And if that all sinks down here to the surface where people live, that's not so great, right? Because we can't breathe carbon dioxide. We can only breathe oxygen. Well, let's take a look at these candles a little bit closer here. And what we're going to do is I'm going to try to pour our invisible carbon dioxide gas out of this giant beaker over the top of our tea light candles here. So let's go ahead and try that out. Look at that. I didn't use any of the liquid from the bottom of this container. I only used that invisible carbon dioxide gas. So this kind of seems right like ice might be the winner. So even though it wasn't in its solid form, that sublimating dry ice gave us that carbon dioxide gas, which was able to snuff out all of our carbon dioxide or all of our combustion reactions, because combustion reactions rely on oxygen, just like people do. And the carbon dioxide was able to snuff them out by pushing all the oxygen out of the way. Now, there is a safe version of this experiment that you could try at home as well. We've done this one on Echo Live in the past, and we call it the invisible fire extinguisher. So check out our website. If you don't have access to dry ice, you actually don't need it because you can generate carbon dioxide gas using just baking soda and vinegar, which are things that we probably already have lying around our house. And we can try the same experiment with adult supervision because we're obviously working with flames and we always want to make sure we're being safe at home. But fun thing that we can try. Now, let's see. Let's get a final vote before our very last demonstration here. Who in your mind has been the winner so far? Who has won fire versus ice today here on Echo Live? Tell me, what do you think? I'd love to hear your answers. I see Jamie asked me a great question. She asked, have I ever had to use this fire extinguisher? And the answer is no. So I never try things using fire without taking the correct safety precautions. So we always want to do controlled fires and controlled explosions, things that we know are never going to get out of control or hurt anybody or damage anything. So I've never had to use it, but that doesn't mean that I don't know how. So I always make sure our fire extinguishers are up to date. And so there's a date written on our fire extinguisher that tells me when this one expires, and I'll have to get a new one. But I've never had to use it, but it's here just in case. That's an important part of science, is always being prepared, even if you don't think you'll necessarily need these pieces of safety equipment. Ooh, lots of people choosing ice. Maybe our last reaction really skewed the audience here, right? Because when we really pitted them up against each other, ice ultimately won out. Some people just can't choose and they think fire and ice, and I am with you. I love both of these experiments, but I figure we'll end with one of the best fire experiments that I know how to do. This is one that we've not ever featured here on Echo Live, so it is pretty cool. It's pretty exciting. It's something new for all of us to see. Now, we've made fireballs here on Echo Live using some different sorts of materials and chemicals. Normally, we'll use something called lycopodium, which is a really, really fine powder, and we'll blow it through the air, and it creates a big fireball. But lycopodium comes from a plant. It's kind of gross, it's yellow, and it only comes from a chemical supply company, which means that it is not food safe. What I have today is a little bit different, similar in some ways, but different in others. What I have is a food safe powder. So this is something that came from the grocery store, and this is going to allow me, instead of using some equipment in order to create a giant fireball, in this case, I'm actually going to do this with my own breath. This stuff is a really fine powder, so even if I were to try to burn it on its own in the cup like it is here on the table, it really wouldn't burn because there's not enough oxygen surrounding all of those particles in order to create a burn or to actually cause fire to start. If we want it to burn, we need to spread the molecules out. We could do this by using something like a bike pump or a fan, but in this case, I'm actually just going to use the air from my own 2 lungs, and I'm going to blow this powder through the flame from my blowtorch here and create a giant fireball, and I'm going to seem like a giant fire-breathing dragon. So let me get my last very important piece of equipment here, because this powder is really gross. Even though it is food safe, it is kind of icky. And so I've got my drink here to just kind of wash it down once we finish this reaction. So let's go ahead. Let's see if I can make sure I aim everything correctly. Let's go ahead with our very last fire reaction in 3, 2, 1. Now that I've washed that nasty powder down my mouth, that brings us to the end of our show here. You tell me in the chat, who did you think was the winner on fire versus ice? I'm a little bit skewed because I thought that last reaction was so much fun, even though it doesn't taste very good. But we are so excited to keep bringing these programs to you every weekday at 2:30 p.m. These programs are free. We will cover so much more exciting science and at-home science experiments that you can try at home. We will be back here on Monday, not tomorrow, but we will be back here on Monday with even more Echo Live. We'll have more experiments to show you, more things for us to do together, and more things for you to try out at home. If you have any questions, go ahead and tell me in the chat. I'd love to answer some before we really sign off for the day here. Tell me who you think won this battle, fire or ice. Tell me what you think. I think I'm going to pick fire because this is my favorite new reaction that I know how to do. But you tell me what you think. Lots of people still picking ice. That's so cool. Maybe we'll have to do some more fire and ice experiments down the road here on Echo Live. Let's see. Jamie asked, can it hurt me? And the answer is fire is extremely dangerous. So the answer is yes, it could hurt me. But like we said, we're being very safe. I've practiced this many times before our program. I'm wearing all my safety equipment, like my goggles, my lab coat, I've got my hair tied back to the side so that it didn't accidentally get blown into the flame. Good questions, everybody. Ooh, lots of people still picking ice. That's so exciting to me. Well, that's about all the time we have today. Thank you all so much for joining, and I hope I'll see you back here on Monday